more or less has experience with a broker. We are a leading scientific instrument and company. We have several divisions from nuclear magnetic resonance (MR). We also have some chemistry and analysis such as FTIR, Raman, and also have a very small division called BEST, which is related to low temperature superconductor and high temperature superconductor, but it's very minor division. And here we are at this nano group, so we focused on nano. This actually includes 3 small divisions, including our nanosurface and metrology. We also include XRD and index DSD. So when we go to our specific division, we call our department is called nanosurface and metrology. So we focused on surface and metrology, but at the nano scale. So when we want to measure surface roughness, film thickness, or other some critical dimensions, we have status profile, optical profile, and AFM. And when we not only look at the topography, but also we want to look at some mechanical properties. We have, in the AFM has a lot of our application in non-mechanical measurement, but we also have, nano indentation system, which is also the best in the industry. And besides topography, mechanical, we also want to look at some nano chemistry. So we have this FMI system, which we'll introduce later. So today I will, because this training is for FM systems. So for the FM systems, we have released some of our models. Most of us are using either multi-mode system or dimension, and maybe some are using dimension fast scan. We also have a product line called Theory of AFM, which is a completely different product system. This system is focused on biology, focused on integration of AFM with inverted optical microscope. So, but for this training course, this we call it GBK Nanovisor Biology product line are not included in this training because, as you see, the design and functions are quite different from our conventional material AFM. So, several years ago, there was a Nobel Prize with 3 focused on 2 techniques. First one is called super resolution, and the second one is called optical tweezer. I think it's from 3 or 4 years ago. And as you know, scanning probe or microscope (SPM) also got the Nobel Prize. But here in this specific product line, we can actually integrate AFM and optical tweezer. And if you want, you can also add super resolution, integrate 3 Nobel Prize techniques into one system, which is a very special one. And after this brief introduction to product line, then we go to the last, which is the nano IR spectroscopy and imaging product. When we talk about AFM, usually we are talking about the surface roughness, topography, nanomechanics, or some electrical properties such as KPFM or KFM. But there's something missing, which is the chemical composition information. But we do have a product line which integrate AFM with IR spectroscopy and enhance its IR resolution to 10 nanometer. So basically we can separate 2 nanoparticles if their sizes are larger than 10 nanometer. We can get the IR spectroscopy at the specific location or particles with 10 nanometer resolution. Here is the people where our partners were supporting this broken nanosurface and metrology. There are more than 40 people now, and this photo was took in our annual meeting in February. So let me see. This is me, and then can't find the 讯号。Okay, Li Jing is here and Suri is here.
Sorry.
Oh, okay. And Liu Yang. Yeah, okay. Well, we have more than 40 businesses. Brook is a big corporation. We have more than 400 employees in China, including mainland and Hong Kong. But for our division, we have more than 40 businesses. And when we talk about the South China territory, actually it's not a small one. We have 10 provinces including Hong Kong and Macau. So from Fujian, Jiangxi, Hunan, Guizhou, Yunnan, Guangxi, Guangdong, Hainan, and Hong Kong, Macau. So it's a rather big territory. And for our team in South China, we have two sales. Beside me, there's Zhang Shun. I'm supporting AFMI and nano IR, and Zhang Shun is supporting nano-indentation, stylus and optical profiler, and also tribology product. We have support service colleagues. Guo Heng, he graduated from South China University of Technology with master in material science, and Dr. Ge Yumei. She focuses on nano-indentation, and we have also Yewi and He Yu. And we also have one application scientist, is Dr. Wang Yang. He graduated from Tianjin University, and supporting now AFMI and optical profilers. So this photo, people in this photo, they are the strong support for you and your lab and your AFM. If you have any questions, if you encounter any difficulties in AFM, either it's operating AFM or how to process this data, if you find something interesting related in your research field in very good publication, you can always approach us and we can have a discussion. Maybe there's something we can help with it. So then we have those people, and now we look at how is the South China territory, the sales in FMI. Here we can see we have got, actually it's more than 3 times of 5 years ago. So we have rapid growth in South China. This reflects the rapid growth and the large government investment in the education R&D in South China. And you can see our new product, a new system installed in 2022 are mostly dimension icon, dimension fast scan. Much more than there are only 2, the small one. So everyone now prefers large platform automatic AFM. And we also have this nano IR, which is relative high value but very specific equipment to solve some scientific problems. And also the nanovisor, we are talking about the BioFM. The BioFM is also growing. So one of the very important reasons of this growth in South China is actually due to this Great Bay Area, Guangdong, Hong Kong, Macau, Great Bay Area. So for the system installed in last year, we have 13 in Shenzhen and 5 systems in Hong Kong. And during this COVID-19 era, the 3 years, our installation, AFM installation in Hong Kong, is close or is around 10 systems. So, and I also noticed that we do notice that there is a very strong growth in Hong Kong in this year and the coming years. But for the last maybe 5 or 6 years, due to different reasons, travel restriction, our local engineer cannot travel to Hong Kong. So we do there's a lack of systematic training in both AFM and other products. So that's why we organize this AFM training for 5 days. This is the first time in Hong Kong we organize such an AFM training, but it's very necessary, and I hope everyone you can take this opportunity and learn something in this during this AFM training, 5 days. Okay. So this is my last slide. Enjoying AFM. So this basic AFM training we has been conducted for more than 7 or 8 years, and before COVID-19, actually there's around 8 to 10 courses. These courses in mainland China, mostly in Beijing, Shanghai, and Guangzhou in group office. But now, since this year, we want to make a change, which is we want to work out from group office, group lab to our user facilities. For example, here we conduct our training in Hong Kong at Hong Kong USD, and we also conduct one AFM training in Changsha. So basically with the open up and the end of COVID, we as a broker, we will give more and more support in Hong Kong, and we are also as our discussion with Dr. Shen Hao, we plan to, after this AFM basic training, we are planning to carry out another AFM advanced training within this year in Hong Kong. And in the first half of next year, we will redo this AFM basic training again in Hong Kong to cover the installation basis, so that everyone is happy with the AFM, enjoying the AFM, and we really hope that Brook's AFM and other products can contribute to your research work, and you are happy with it in daily life. Okay, thank you everyone. So next, Dr. Shen Hao will give a brief speech about several minutes, and then our training partner, old friend Alex from Tech will also maybe speak for several minutes.
Okay, good morning, and I'm China Service Manager of Brook Nano Services Metrology Division, and my name is Sun Hao. It's great to see so many teachers, students today here to attend our training, and I am based in Beijing. When I arrived Hong Kong yesterday, I found the weather in Hong Kong is very nice. Because you know, in Beijing, the highest temperature a few days ago is 41 degrees centigrade. And in Hong Kong, it's only 31. I feel very comfortable. And I also found the training facility provided by the HK UST is so great. We have so large training classroom, and we will have a real tools for hands-on practice. I also see so many people here, and I can see your passion for learning. So we have good weather, we have good place, and we have good people. Let's make the training successful. And I also would like to express my apologize for the inconvenience caused by the pandemic. Because in the past 3 years, our team was not able to come to Hong Kong for face-to-face communication with you. We do know the pain, and we want to change it. Now, with at the end of the COVID, I think everything is back to normal. And to make up for the lack of face-to-face communication, we decided to hold this offline customer training here today. And I also hope this training can be our new beginning to support Hong Kong customers. We can interact more efficiently during the training with each other. And you know, Hong Kong and its surrounding cities, Guangzhou, Shenzhen, are very important markets for broker, as we said. And now we are investing more and more resources to support the customers in this region. In the past few years, the number of engineers in this region has increased from 1 to 5, and now we are hiring 2 more engineers. One of the engineers will be on board the next week. And we also plan to hold 2 to 3 customer training classes like today's training in Guangzhou, Shenzhen, and Hong Kong, at least 1 in Hong Kong every year. And this year we also have another advanced training, as we said. We also want to conduct some customer return visits in Hong Kong. And to help our customers better use and understand our instruments, my team also created a lot of training materials, like training videos, FAQs. And I think Dr. Liu Yang will introduce these service resources to you later. Now, back to the training. Our engineers, Dr. Liu Yang, Shu Rui, the senior trainers, will spend the next 5 days with you. And I hope everyone can communicate with them and get your technical issues solved. So thank you all. Thank you for coming, and thanks for the great support from HK UST and Theory. And enjoy learning. Thanks.
Good morning, everyone. My name is Alex from Theory, broker channel partner in Hong Kong. First of all, I really would like to give a very special thanks to the very strong broker team that visited us this week. I think we have been in very difficult situation in last 3 years for the COVID, and I'm so glad that after we have the COVID release, we can have the Booker experts to come in visiting Hong Kong to give a more advanced support. And I believe that the users in Hong Kong are very smart. Together with the strong application and experience from the Booker team, like from Dr. Sun, Surrey, and Dr. Liu Yang. And I believe that we can do a very good job in training all the AFM users in Hong Kong. Not only this week, but I believe that it is a very good beginning to start supporting the customer on site in Hong Kong so that you guys can all enjoy the AFM and at the end can publish a lot of good papers. Okay, thank you everyone.
Good morning, everyone. My name is Yang Liu, and
Hello? Yeah.
okay. Hi, everyone. My name is Yang Liu. I'm from Brooker, and it's really great honor for me to come to Hong Kong and have a discussion on AFM technologies with you guys. And it's my first time to Hong Kong. It's a really beautiful city, and I enjoy the campus very well. Okay, so our plan in this week is we will discuss some AFM technologies and share something of AFM and its basic applications, including force and electronics with you guys. And we will do, our plan is we will do a theoretical discussion in the morning, and then we will have a hands-on session in the afternoon. And thanks to MCPF and give us these opportunities to discuss the FM with you. And so as a tradition, we will introduce our DNSM service sources with you. So give you a way how to reach us when you need help about AFM. So when I'm in PhD, I'm also doing some AFM stuff in my universities, and in US we don't have such resources like in China. And when we have some problems with my AFM, I remember at one night my AFM pops out an error, something about the sensor again. Yes, and at that time we don't know what that sensor means, but it gives an error. So what we can do, we are just students, and in the next morning our professor will come say, hey, what's wrong with your AFM? Why you give me nothing? So at that time we have to reach the US guys with emails, but they don't reply emails at night, so I have to wait. And then I come to the office at 8 a.m. the next day, and well, they have replied me an email, and they send me a long notes about how to disassemble all the FM and then test some points with multimeter, blah 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 stuff. And then and then I spend the whole morning about that to test my FM and then I send the result to him. And wait another day, we do the same back and forth. It's just a waste of my time. And but nowadays in China, you have Booker guys with you, okay, and they can provide you more remote support and try to save you days, try to save your life. even at night, we cannot help you. You have the same thing as me. You crash the scanner, you crash the sensor, your computer is down. Okay, you have nothing to do, but at least there's some guy can tell you, okay, calm down. It's just an AFM. It's not your whole knife. It's just a cracked AFM. It's fine. Okay, so that's what we try to do. Okay, so the point of this knife is just to give you the point how to reach us, how to find broker when you need. Okay, so Broker Corporation and Dr. Chen and Alex and Dr. Sun gave you a great introduction about our corporations and told you how good broker is. Okay, yes, we all know that. Yeah, and it's a quite aged corporation. It has many good instruments, and the point is we try to help you to establish a good results. And for China service resource, we established in 2010, and nowadays, under the leading of Dr. Sun, we are a big group now. So try not big enough to have all the customers in China because there are so many instruments, and we spend almost every day to reply phones and emails and messages. And now we have this is about our team, and most of you have met these handsome boys and girls, right? And we have mainly about 4 teams. One is about AFM's field service teams. It's just to provide you basic training and the installations. And some of them, and we have another team, and Chim boys leading by the TMT and as the tribology and the scanning optical microscope team. And then we have a customer support team in China. We will provide you technical support, and sometimes you need to bug us about the repair things. And we have the administration teams to help you about your commercial things and send you some quotes or something. Yeah. And here is the takeaway page. I think it's about our support resources. So we try to give you the instant support through some AI. So nowadays we are using the phones and messages, and in China we have the WeChat and WeCom. And hopefully in future we will do some AI stuff. And for the hardware things, we can do the tests and the repair things in China nowadays. We don't need you to send your instrument back to US again. No, you can just do the repair and the test just in Beijing and Shanghai. And we also establish a local language database because AFM, there are so many tricks about how to adjust the parameters, how to prepare your samples, and some days it's not on the textbook. So we make some short videos about this, and we all put them online, and if you need, you can check them online. And of course, we found we public our resources just mainly on Bilibili and on the WeChat the platform. There's no ads. And of course, you can send it to our factory for the repair or replacement. Okay, and here is our post. It's about our service, technical support resources. You can reach us by phones, emails, or you can just join our WeChat or WeCom groups, and you can reply messages. You can just send us messages in the group, and we will reply almost 7 times 24. Okay, and we also have a customer care center now we are in Beijing and Shanghai, and our main job is to reply your messages, provide technical support, and we just do the test and repair things, and some of you may have reached me or Shui about this. We can do just the test and or repair locally. And we also provide the training for our customers, mainly about the AFM, and in every year we may also have advanced training about the force or electronics, and hopefully in future we can cover other stuff. And we establish a local knowledge database on just a platform called Yuque. And on that, we establish a menu in Chinese, and we have frequent ask and questions, FAQs on that. So to help you, give you a brief guide about the AFM usage and applications. And yes, we have the online training courses, and most of you have learned Dr. Sun, and by through this way, you just say just watch his videos about how to use AFMs, and his AFMs is his lectures. Each lecture is about 2 or 3 hours. It's just it's good to join, right? Okay. And we also made some short videos about about the small operations or troubleshooting. You can just substitute and follow us on that. And we also public papers with customers, and we would like to focus on customers. Advanced research to say how you guys use this AFM, because this AFM is invented by researchers, and it's used by researchers, and hopefully we can continuously develop this instrument by our researchers. And yes, we have the local part stock. So if some of your small parts failed, like some screws, like some cameras, like some things, just tiny stuff, you don't need to wait from US, and just we will ship it out from Beijing or Shanghai. Okay, that's all about our resource. So, and we will share this slides to you when the lecture is over, and I also make the records so we can also share to you. If you need, you can find the slides to reach us. Okay, then let's start the AFM stuff. Okay, so about the AFM stuff, most of you have learned this name. Maybe you will learn another name that's so-called the scanning probe microscope. So, when I learned this kind of technologies, I just ask the question: okay, what's the microscope? The microscope, in my understanding, is just some glass things, and we make them kind of pack them as an instrument, and we want to use this thing to read or to say tiny stuff. So that's my understanding of the microscope. Okay, and this microscope, and we have established lots of fantastic instruments. Like you use today, it's all kinds of optical microscopes, and this optical microscope, after long times development, is almost it's still growing. But usually, when you talk about the microscope, you use the same way. You use some way to let you help you to see the tiny things. And this optical microscope, nowadays we would say it has its limit. Okay, so when we talk about the optical microscope, we actually want to say is we have some stuff and it will give out some lights, or it reflects some lights and it goes into your eyes. Nowadays, of course, it not go to your eyes, it goes to a camera, and then you can see this tiny stuff. So we use the optical way to enlarge the scene and to achieve the microscopy. But it has its limit. But in all this, we don't know this kind of optical microscopy, because we say the light is kind of continuous things. But as we go in, when we reach the 20th century, we know, okay, no, maybe the late 19th century, we know the light is not that pure, it's just electromagnetic wave. So as a wave, it has the same, we all know, is the diffraction. So due to the diffraction, it gives us a limit. Because mainly for the optical microscopy, mainly we used is the so-called the visible light. The visible light is wavelength range is about from 400 nanometers to 800 nanometers. So due to its diffraction, we can only say its resolution is about maybe 100 nanometers. So let's think things like this. So nowadays, in all this, we have two cells. We all know cells is in the size of micrometers, right? So we have two cells. We want to say how the dendritic cells touch the T cells. Okay, so this is the T cell. This is the dendritic cell. Okay. So the cell is about tens of micrometers. So the size is 10 micrometers, about 10 micrometers. Maybe this is also 10 micrometers. So we want to say how the dendritic cells touch the T cells. Okay, we just use the optical microscope to watch that. No problem, right? But in 20th century, we have locked the door of atoms. We want to know how the things happens at the molecular scale or the nanometer scale. This is different. So we try to study something called fret. Okay, we have molecular A, we have molecular B, and when it touches, it gives us the illumination. It shines out some fluorescence. Okay, so for this phenomenon, we all know the molecule is at the size of nanometers. Okay, so we just assume it's large molecules. So this one is 5 nanometers, this one is 5 nanometers. So when it touches each other, it gives us some chemical things, it gives us out the lights. So at this scale, we try to study how it touches each other. And then the story is different. Because we are using optical microscopy to state a molecule at the size of 5 nanometers and the optical microscope, due to the diffraction, you cannot say a dot at 5 nanometers. Instead, you say a large spot around 100 nanometers. This is due to the diffraction, because our visible light is just such long wavelengths, the electromagnetic waves. So we do not say a dot anymore. Instead, we say a large span. Okay, so at that time, the molecule A and molecule B, they touch each other. The distance between these two molecules is maybe just a nanometer scale. But nowadays, if we try to watch that with the optical microscopy, you see nothing, right? You just say a large spot. You can say no details about molecule A, nor molecule B. So that is because due to the diffraction, we cannot see the molecules, and so the diffraction set a resolution limit for us. We cannot resolve these two molecules anymore. It's not the story we study the cells. Okay, so these things become more and more important in 20th century because we just want to study how things happen at the molecular scale or nanometer scale. So we need more messages to help us to see the details. So we need a new microscopy. Okay, and then we all know in 20th century, at the beginning of 20th century, we have a revolution of quantum of the quantum quantum stuff. So nowadays, after that, we know the real thing about the electrons and the photons. So we can use electrons to develop a new microscopy. That's the electron microscopy. The electron microscopy is we do not use the light, the visible lights, as our things to see things. We use electrons. That's the electron microscopy, which is nowadays is famous is the scanning electron microscopy and the transmission electron microscopy, which is SEM and the TEM. And for them, we do not use the lights. Instead, we use the electrons. And since the electrons is small particles and its wavelength is way smaller than the opticals, so it can break the diffraction limit to see the things. That's our SEM and the TEM. We give a brief discussion about the SEM. Where is the this one. So you guys are quite familiar with the electron microscopy. We just give a brief introduction. For example, for the SEM. For the SEM, we know our atoms is just many layers. It has inside it has electrons. So if you have another electrons, if we accelerate these electrons to high speed, it will work like a bombard, and it will just crash on our atoms. And it will crash on the atoms. It gives out the energy to the atoms, and these atoms will emit some electrons, and we call these electrons secondary electrons. And if this atom has more electrons, it will give out more secondary electrons. So the density of secondary electrons is related to the atomic number of our atoms or atomic weight of our atoms. Okay, so that means more heavy atoms, it will give out more secondary electrons. So we just detect these secondary electrons. We can know these things. So light atoms and heavy atoms will give us different contrast. So we can use this density of the secondary electrons to differentiate different atoms, so we can differentiate different substances, and so it gives us a view of our materials. And since this is just caused by the secondary electrons, and we use the electrons to shine the subjects, it gives us a high resolution. So that's why it can reach high resolution using the electron microscopy. But from this principle, we can say you shine the surface with electrons. It gives out secondary electrons. So it only gives you the distribution of atoms on surface. So this is a two dimension microscopy. So it cannot give you the depth stuff. So that's why you say your message under the SEM or TM, it looks like, it's kind of 2D things. So if we, like in nowadays, we have the nanotechnology or microtechnology, we would establish some trenches. And these trenches, we make them the depth around nanometer scale. We want to say how the depth looks like. The SEM cannot give you such thing. So how to do that? Of course, people are smart. They will just rotate the sample to say how it's saturated, right? But its principle, it cannot give us the depth information. It cannot give us the information at the 3D, at the three-dimensional. And the same things is in TEM. TEM is not secondary electrons. We use the electrons to transmit the things to give us the transmission. So it's the same, but TEM has higher resolution. But its principle is its limit is this is the 2D microscopy. It cannot give us the depth things or the Z scale things. So and after that, when the time reaches the late 20th century, we need something. Okay, we want to study the things at molecular scale, and we also most of our stuff does not interact with each other just on the surface. We want to also understand the three-dimensional things. So it gives us a requirement. So we need to learn the things at a nanometer scale, and we want our study to be 3D. And sometimes we also want to study our things in for example, some biological stuff. So it's better to be in vivo. So that's our three requirements. Okay, the optical microscope can do 3D, can do in vivo, but it has a resolution limit. The EM is so good, right? Pretty good at the resolution, but it's hard to give us 3D information. And of course, it's quite difficult for the in vivo study. So that's the requirement at the late 20th century. Okay, so we need some instrument to give us to fulfill these three requirements. So those guys from IBM, they just think about how the people study the outside world. We do not just use our eyes. We also have hands. We can touch our stuff. We can just use our hand to touch the surface and to reach how to feel how it looks like. We do not say it. We just feel it. So at that time, they try to develop an instrument. Okay, so we use touch to feel the things. And then let's think about this process in details, how it really happens. Okay. So we have something on the surface. So we have a surface morphology thing. And then we want to know how this surface looks like. We can just look at it, right? It reflects lights, or it itself can emit lights. The light goes to our eyes, and it gives us an image just on our retina. That's the traditional way, and we use this way to establish the optical microscopy. But we can also to touch the things. And how this touch things feel the surface works. So actually we use our finger, and we use our finger to reach the surface, and then we move our fingers, and in this movement we keep our finger touch the surface. And at that time, when we move our fingers on the surface, we can feel how it looks like, how the surface up and down, up and down. So we just make these things more in a more physical way. So we keep in touch, and then we move. So, and then this will give us is topography. Okay? What's the keep in touch? So the keep in touch, we just press our fingers on the surface, and then that's keep in touch. But when we think about this so-called keep in touch, we are just talking something is we keep the distance between our finger keep the distance between the finger and the surface are the same. So the so-called keep in touch, we can use a mathematical way to describe is the distance between our finger and the surface. We want to make it a constant. So if we make sure our the finger and the surface, the distance is the same, it is a constant, so we are actually we make them keep in touch. And then during our fingers movement, since our finger is keep in touch, the distance is a constant. So this topography is actually the trajectory of the finger. So we can use the movement trajectory of our finger to represent the topography. So how we know these things? You store them in the brain. So with this way, they can invent such an instrument. So this is our big picture how to retrieve that. So sorry, I just can say it right. Okay, we can say it. Okay, so we use some tip, and we use the tip to touch the surface. How to achieve that? We just make sure the distance between tip and the surface to be the same, to be a constant. And then we move the tip on the surface. And after that, in this process, we record the movement of tip in the software, and the movement of the tip in the software, which we will say this is the topography of our surface. Right? That's the main principle of the scanning probe microscopy. So our scale, our objectives, nanometer scale, 3D, and in vivo. 3D, of course, it's of course 3D. We move the probe in the XY surface, and we record its movement also in the Z direction. So we achieve 3D. In vivo, it's fine. We put the samples in the in vivo conditions, and we put the tips also in the in vivo conditions. So it's of course it's in vivo. So the last thing is we want to reach nanometer scale. If the tip is nanometer, if the sharpness of the tip is at the nanometer scale, we achieve the movement at the nanometer scale, so we can reach the nanometer scale. So the only things we left is how to reach the things at the nanometer scale. So this distance between sample and the tip, we need to make it nanometer scale. Okay, so the things is we just try to achieve to keep the distance between tip and the sample at constant, and this distance is nanometer scale. We achieve that, we achieve the SPM at the nanometer scale. So the last question we have is how to keep the distance as a constant at the nanometer scale. Okay, so we don't need that. So how to control or how to control the distance at a constant? So we think about our daily life, how to control the distance. The thing everybody quite familiar with is we do the driving. Okay, so the driving policy asks us we need to keep our distance between your cars and the cars in the front at a safe distance. So we need to keep the distance. So that's my car. That's somebody else's car. We want to keep our distance at the same at a safe distance. So we need to keep this distance. For example, we need to make this distance, say 550 meters. How we achieve that? So you are just drive your car and you use your eyes to measure your distance with the front one. So you use your eye to measure the distance. And then you get the distance, and then if you find, okay, this guy is just a brake on just tap on this brake, so his speed is slow down. And after slow down, you will say, oh, I'm almost crashed on them. I need to increase the distance between me and him. So what you will do, you will also to decrease the speed. So this way, we just try to establish a so-called loop. This loop is we want to measure, we want to keep the distance as a constant. By how? By control the velocity. So the velocity is we control that to achieve the distance at a constant. And then we need to measure the distance. So we use our eye to measure the distance. That's a quite simple loop. Okay, so we use the distance as the same and send it to our brain, and then we use the brain to control the speed of our car. So that's a small loop. So when we want to control the distance at the nanometer scale, we will do the same things. We will just lift or bring down our tip to make them up and down, to make sure the distance between the tip and the surface are the same. So we will just use our instrument to control the height of our tip. That's simple. To control that's simple. But the only thing in this loop is you want to watch or you want to measure the distance, right? If you don't know the difference, the distance, how you control the distance as a constant. So the key point here, we want to control the distance at a constant. We need to measure the distance first. Okay? So the story make a small change. Is we want to control the distance. We need to measure it first. If you want to make the tip touch the surface, say the distance is 0.1 nanometer, you want to control the distance is 0.1, nanometer, how you always reading the distance and then you move the tip up and down, up and down, up and down to make it 0.1 nanometer. That's the point. Okay, so let's think about the way how to measure the distance. Okay, how to measure the distance in the late year of 20th century. We will watch back how to measure the distance. Okay, optical microscope, no way, we cannot say the distance. Electron microscope, okay, that's good, that's good. So you want to measure the distance, you will by how? By example, electron microscopy inside our SPM and using the electron microscopy to read the distance between tip and the surface and then control that. Sounds stupid, right? We want to invent a new microscopy independent of the SEM or TEM. We don't want to put the SEM or TEM inside our new instrument. That's a waste, right? So we need to another way to measure the distance. Okay? So how? Okay, the IBM guys just think about, we want to control the distance between the tip and the surface. We only need it to be a constant, but it's 0.1 nanometer or 0.15 nanometer. Doesn't matter to me. I just need to know it's a constant, that's enough. So they think about, okay, I want to make this same as a constant, but I don't really need to know what exactly it is. So in those days, they think about, okay, I do not need to know the exact number. I just need to make it the constant. So they think about another way. If we can find a function, if we can find some physical things, if this physical things is a function of distance, and we keep this physical things as a constant, that means we control the distance as a constant. So they make a change. They don't do the measure, but they measure a function of distance. And we want to make sure this function is a constant. If we find this function, everything is solved. We get a nanometer scale. Okay, so at that time, what's this function? Okay, the first function they use is the so-called tunneling current. Okay, the tunneling current is a quantum thing. So we just do a brief introduction about that. Okay, in all days in 19th century, we think the electrons is just a kind of particle, it's a bulletin. When it hit on the surface or on the wall, it can just hit back. So it will just rebound back. So we call it reflection. So if our electrons just hit on a wall, it hit on that, it will just rebound back. That's the classic, the classic physicals told us. But in 20th century, it tells us another different story, that the electrons is not just a particle, it's a kind of wave. So if this kind of wave, it can behave like a wave. So the way we know we have a diffraction. So since it has a diffraction, you can say this wave can go somewhere beyond this wall. So this is the quantum thing. So it just it can just like a wave to beyond this wall. So let's say how this wall looks like. Okay, so we all know the electrons is just bonded in the atoms, and in the atoms, the electrons is just feel the attraction force from the nucleus. Okay, so and then we can use the quantum chemistry or quantum physical things to calculate its energy, and its energy is always negative, right? So in the atoms, it's a negative energy, so the energy is negative, and then that's our. Let's say this is okay. Let me just in this way. Okay, it's energy here. This is energy T. So, no. Let me watch in this way. So this is the tip, this is the surface, and its energy level. Let me say, okay, this is energy level. This is the E tip. We make them. It's negative because the electrons is bonded in the tip, bonded in the atoms, and the energy level on the surface is also something like this. Energy on the surface is also negative. Okay, so if we do not let the tip touch the surface, there will be a free space, and this free space or the similar or in the classical or in the accurate way, we make them vacuum. If it's vacuum, we all know in our physics that energy in vacuum is 0. That's the E vacuum. Okay, so the electrons inside the tip is bounded by the atoms and bounded by the nucleus, so its energy is negative, and on the surface it's also negative, but in between the space the energy will be 0. So we establish a potential wall. And these electrons follow our classic way. It cannot go from tip to surface because it's a particle. But in the quantum way, we think it's different because it's a wave. So it can go from the tip to the surface. And this behavior you guys are familiar with. You just use the Schrödinger equation to solve that. You can get how it goes to the surface. Okay? So if the electrons from tip goes to the surface, and this way we use the Schrödinger equation to solve that out. But in a way to watch it macroscopically, the electrons goes from tip to surface. It means a current from surface to tip, right? So we want to say we want to control the distance, but when we look at this in the quantum way, okay? If the tip goes from, if the electrons goes from tip to the surface, this behavior, we will use the Schrödinger equation to describe that, and we will use the wave function to solve that. You can get the wave function out, but in the macroscale way, we say a current. So our current is related to how the electrons travels, which is the wave function, right? Use the Born stuff, you can just calculate how what's the possibilities for this transmission. Okay, so this wave functions should be what? Should be a distance between this potential wall. If the tip is get closer to the surface, it will be easier for the tip to go to the surface, it will be higher possibility for this transmission, and then it will be higher current. So in this way, they establish finally they find a function of the distance. So if you control the current as a distance, you actually control the distance between the tip and the surface as a constant. And then to measure current is more easier than to measure the distance at a nanometer scale. So they use this way to establish the so-called scanning tunneling microscope. So we draw it in this way. We have a tip and we have a sample surface, and we just use our we just use a current amplifier, or we just use a say to measure the current between the sample and the tip, and then we get the current out, and then we use a controller to control the current at the between the tip. We control the current as a constant by how? By move the tip up and down, up and down, and then at the same time we move the tip at the XY surface, and we record the trajectory of our tip, and then we get the so-called the morphology of our surface. So it's something like we measure the current, and we move our tip in Z direction. And our goal is to make this current as a constant. And so we establish this loop. At the same time, we move the tip in XY. By this tool, we can get the movement of tip at X, Y, Z direction. And this movement, we record that in our software, which equals to our sample topography. That's how the STM works, which is our first scanning probe microscopy. Okay, so it's the main principle is quite easy. It's just our childhood years. Yes, please.
You mentioned that all these happen in vacuum, but in our AFM, how can we apply the vacuum? Actually, you don't apply the vacuum on it, right?
That's good question. But in the STM, in all the way in the tradition, in ways invented, they put them in the vacuum. But even if we put that, even if we don't use the vacuum, that this energy level will be slightly lower, because the L is not as the same as the vacuum. There is some the oxygen and the nitrogen in the atmosphere, but its level it's not as the same as zero, but it's just slightly lower. And only when this energy level of our air is just higher than the energy level of tip and the sample, we can still establish this potential wall. You have the potential wall, you have this stuff, and then you can use the Schrodinger way to calculate its wave function, and then the things still the same. Okay, so the STM in vacuum or in L, in the physical difference is just here. It's just here. Of course, there are more. There will be more. There will also be some difference in the experimental art. In the theoretical, the difference is just here. The L energy is slightly lower than vacuum, but it can still give us the potential wall. And it gives us the potential wall, this loop works. And we can get the current, and from the current, we control the current, we control the distance. And then we can move the tip. That's give us the STM image. Okay? So this is our the principle of the STM, and this is the first scanning probe microscopy. And in that days, they just need to find a sharp tip. That's the only that's the only job they need to do. And of course, it's easy for them because our methods can easy to make a quite sharp tip. And so using the STM, they can watch, they can see the atoms at the first time. So of course, they won Nobel Prize just 4 years later. It's so good. But then we see a small problem here. So in our way, when we watch back on this loop, we want to control the distance. And this distance is a function of the possibility of the electrons transmission. And this stuff is just from the quantum, it's just from our quantum way. So we calculate the wave functions following this potential wall, we get this same stuff. But there is one leakage here. Does the transmission of electrons means we can get the current? The answer may be no, because the possibility is always there. Once we establish a potential wall, the electrons can't go from tip to surface. That's the wave. That's the Schrödinger equation. We can always solve out the wave function, and we can always get out its possibility. But there is a problem. If our sample is insulator, it's not conductive, then we cannot get the current at the macro scale. Of course, the electrons is always from tip to the surface. That's the way. That's the quantum theory tells us. Yes, is always there. This thing is always there. The possibility is always there. But the possibility does not mean there is always a current. The current requires the surface of sample to be conductive. If the sample is not conductive, you have everything. You have the tunneling electrons, but you don't have tunneling current. So the STM gives us a quite large limit that our surface need to be conductive. But no, not every surface is conductive. Okay, that's the similar problems you have in the SEM or TEM. You try your best to make your sample to be conductive. You just spread some carbon or gold on your surface to make it conductive. And the same thing comes back to the STM again. But we have so many stuffs which is insulated. We want to measure the surface of many stuff. Biological things, polymers, no, they are all not conductive. They are all insulated. We cannot get the current for those samples. So how? So let's go back. The movement is correct. The control, the distance principle is also correct. The only things give us problem that is the function. If we use the tunneling current as this function, we have to make the surface to be conductive. So the problem for us to image the insulator is we need to find another function. And this function, we will say, we call it a force. Okay? So let's take maybe a 10 minutes break, and then let's back to go to the AFM. Okay? we just discussed something about the scanning probe microscopy. So we need to find a microscopy to study the nanometer scale at the three-dimensional topography, and hopefully we can watch that in vivo. And that's our goal. So to achieve this goal, we establish a scanning probe way to get the topography. By how? We make the tip to move it in the XY surface. At the same time, we keep the tip in touch with the surface, which means we control the distance between tip and the surface as a constant. And during this movement, we capture the trajectory, the movement trajectory of our tip at X, Y, Z direction. And such, we record its trajectory, we get the surface topography. So the only left physical things is how to control the tip sample distance as a constant. To control that, we need to measure that, and to measure that is a stupid way. So we don't measure the distance directly. We find a function of tip sample distance as a way we control this function as a constant to do that. The first function we found is the tunneling current, because there is a tunneling effect between the tip and the sample. If we lift the tip up a little bit, in the old way, in the most classical way, we do that in vacuum. But of course, we can also do it in the atmosphere. And by that, we lift the tip up a little bit, we establish a potential wall. In this potential wall, the electrons will transmit this potential wall following Schrödinger equation. And from that, we can calculate its possibility density. And from this possibility density, it means the electrons goes from tip to the surface. And at macro scale, we say a current. If we control the current as a constant, we control the distance as a constant. So we establish the STM. By measure the tunneling current, we use that to control the movement of the tip at the Z direction. And then we move the tip in XY direction. Finally, we record the movement of tip at X, Y, Z scales, and we capture the topography of the surface. That's the STM. But this STM requires us to measure the tunneling current. But tunneling current is not always there if our surface is insulated. So we need to find another function. So the second function we try to find out is, it's just the same. So what function is also what's saying is also a function between of the tip sample distance. We think about that, we found out, there may be a force, and which is more similar to the touch wave. When you touch the things, you feel some pressure. The pressure gives by the sample gives to your finger. That's pressure. And when we think about this pressure in more physical ways, we now understand. What's this pressure comes from? In the physical ways, so we all know all our tips or samples, they are all a bunch of the atoms. So these atoms, they have a nucleus, and it has lots of electrons outside. So once these two atoms touches each other, they feel something. First, the electrons will be a repulsion force between electrons. And the second, there will be a repulsion force between the nucleus. And this repulsion and also they can feel some attractions between the electrons to the nucleus and that, right? That's the way we feel some force between the atoms and between two atoms. So this thing we can write it down, okay? So it's the force between nucleus, and second, the force between electrons. Okay? And when these two atoms get too closer, we can also get something force, get it out from the Pauli repulsion, right? Pauli repulsion. Okay? So all these kind of things, they all related to distance. If you get it closer, all this force will increase. So we reach out, we realize that, okay, if we don't think any current things, we just consider the force from nucleus, electrons, and the Pauli repulsion. They all just tells us, okay, there is some force between the atoms of tip and the sample. And this force is a constant over distance. So if we use a force, that's maybe our final goal. Okay? So they think about this way. We don't control the current anymore. We just need to control a force. So if we control this force, we can get this thing out. Similar thing as our STM. So we control the force and we make the force as a constant. Okay, so the left story is how to get the force down. Okay? So the thing is, we have a tip, we have a sample, and there is a force between tip and the sample, and we call it FTS, tip sample interaction force. And this force, we know is this stuff. They are all electron stuff and some Pauli stuff. It's fine. It's just a force. And then we know this force is a function of distance. It's a distance between tip and the sample. And our goal is to control tip sample distance as a constant. Means we just to make this one as a constant. So we need to control the force. And then the next question is how to get the force. Okay? So to get the force in all this, you want to measure force, you just need a scale, right? And this scale is kind of cantilever, it's kind of lever. So we need a scale to measure the force here. So how we do that? Okay, this is the tip, and we get a force between tip and the sample. And then we put the tip on a scale. Okay? And this scale is just used to measure this force. Okay, so what's the scale? We just attach our tip to a lever, and we make this lever to be fixed on another side. So it's just like a cantilever. The one end is free to move, the another end is fixed. So this is a cantilever. So once the tip feels a force between from the surface due to this stuff, so it will cause a force at the tip. So this force at the tip, it will cause the bend on this level. So the bend of the cantilever is just related to the force between tip and the sample. So we can do something like this. our goal is the distance between tip and the surface as a constant. To do that, we convert this into tip sample interaction force, and we make them as a constant. And then we cannot get the force directly. We need a scale to measure that. So we transfer the force into the band of the cantilever. And so we call this band as deflection. So the deflection of cantilever is a constant, which is a function of the force. So finally, again, we want to control the distance, we convert it into force. We want to control the force, we convert it into the deflection of the cantilever. And finally, we need to measure the deflection of the cantilever. Okay, so how? To reach that, we want to ask a question, okay, how large is this force, or how large is this deflection? Okay, so let's do a quite rough mathematical here. Okay, first, our final goal is to control the distance. So what's this distance? We want to reach that in the nanometer scale. So this distance is about a nanometer. What about the force? So the force, mainly the force is about the electronic things. It's the electric force between electrons and the nucleus and plus some repulsion stuff. So no matter how, it's the electromagnetic force. So this force, we can just use Coulomb equation to calculate that. Right? What's the Coulomb equation? There is a constant K, and there is a quantity of charges for tip and the sample, and that's the force, right? So we just do a rough calculation here. What's the quantity of charges on the electrons? We'll know there's 10 negative 19 coulombs, right? So it's 1.6 blah blah blah. We don't need to worry about that. What's about the charge on the surface? It's something also like that. So it's 10 negative 90. What's the distance? Nanometer scale. So it's 10 negative 9, and it's a square. Okay, so what's the quantity of the Coulomb constant? It's about 10.8. So this force will be 10 negative 19, so this is almost gone, and this one is almost gone. So it's roughly about 10, 11 or 10. So this force is what? It's piconewton. Maybe goes to the nanonewton. Right? That's the force. We do a quite rough calculation. It's at this scale. So to control the distance at nanometer scale, this force between tip and the sample, we do a rough estimation. It's about nanonewton to piconewton scale. So this small force will cause a band of the cantilever, and we know this kind of coefficient is the stiffness, and the stiffness is maybe at 1 Newton per meter, maybe goes to 100 newtons per meter. So the deflection of the cantilever will also be nanometer to picometer. So again, we want to control the distance between tip and sample as a constant. We finally goes back to we want to measure the deflection of cantilever. But again, this distance is also at nanometer scale. How to measure that? No, we don't have a way to measure the distance at nanometer scale. So what we can do, we enlarge this distance. By how? By a level again. So we shine a laser on the back side of the cantilever, and this band of the cantilever will cause the deflection of the laser beam. By measure the laser, if we make the laser beam this end to be larger, we will enlarge the band of the cantilever. So finally, we use a laser beam to enlarge the cantilever deflection. So that's the final stuff we invented on the AFM stuff. So the point is, we just give it a review again and again. We want to control the distance between tip and sample as a constant. We convert it into the force between tip and sample. To control the force as a constant, we use a cantilever to measure the force. We convert the force to a deflection of the cantilever. But again, the deflection is so small. So we use a laser beam to enlarge the deflection. And so finally, we are looking at is the laser beam signal. And this laser beam signal is just tells us the distance between tip and the sample. And this thing just gives us to make this thing as a constant. So we don't need to know the laser beam signal's absolute value at all. We just to make sure this laser beam signal to be constant. And so we record the laser beam signal, and then we use the laser beam signal to control the movement of tip at the z direction. At the same time, the tip is moving at xy surface. We record its trajectory at x, y, z. We finally get the topography of the surface. That's our way of AFM. Okay? It's complicated, it's more complicated than STM, but it gives us, but enlarge our application. We can do that on the insulated surface. We don't require the surface to be conductive anymore. Okay? That's the AFM principle. Okay? Any questions about that? Okay? Quite simple, right? It's just the most difficult part is of course here is about the force. That's the most difficult part. But besides that, it's just a quite direct way to get the same. Okay, so we get the principle. We will just go down to how to achieve the same in engineering. Okay, so the principle is like this. So the physicals just finished. So the physical scientist has finished the way. So that's the way to do an AFM. That's it. And then engineer need to find out how to achieve this stuff. So we will just discuss the same in the engineer way. So the engineer way is just how to achieve this thing. So to achieve this thing, we can just separate this job. Okay, so let's finish this stuff. The K is to keep the thing as a constant. By that, we convert into the laser beam signal at constant. This will control the movement of tip at z direction. And then we add the move at xy direction. We send all this thing into the software to get the topography. So that's the AFM principle. In engineer way, there are two things we need to conquer as engineer. First, how to measure the laser signal. Second, how to achieve the movement, right? The laser beam signal, we need to measure that. We want to make sure this thing is really related to the deflection. So that's the laser stuff. Second thing, okay, the physical scientist said, okay, the tip is moving in X, Y, Z direction at nanometer scale, but how we achieve that as engineer? So that's two engineer problems we need to conquer, and let's discuss from here. Okay, so this thing is just give you some brief introduction about how the basic components of our AFM, and you're all familiar with that. So we don't spend some time here, and we will just watch at them when we on the hands-on session. Okay, so let's go to the laser stuff. Let's conquer the laser stuff first. Okay, so this laser stuff is just used to enlarge the deflection of the cantilever. So this laser beam is just to raise the deflection of the cantilever. So let's think about it this way. So we have an AFM tip, and then there is some surface beneath the AFM tip. And once the surface touch the AFM tip, it gives us a force between tip and the sample. And this force will cause the band of the cantilever. So the cantilever gives us some deflection signal. Okay, so this deflection will be enlarged by the laser beam. So we try to read the laser beam signals, which represents the deflection of the cantilever. So how? So these engineers finally think about, okay, let's just figure out some detectors, and these detectors can detect the laser beam signals. So they just put a position detector there, because we shine the probe on the surface. We shine the laser beam. We shine the laser beam on the cantilever, and it will reflect the laser beam to somewhere. And we place this position detector at the path of the laser beam. If the cantilever bends, which means there is a deflection of the cantilever, it can bend the path of the laser beam, and then we just need a position detector to tell us, okay, what's the position of the new laser beam source? Then that's it. So we just put a position sensitive detectors on the path of the laser beam, and use that to read the position of the laser beam on the detector, and it will tell us how the cantilever bend. That's the story. So the first thing is quite simple. Okay, so by how? Okay, so we try to read the position of the laser beam at the photo detector. So this thing is just a 2D thing. At a 2D surface, you want to know a position. You just need what? You just need two numbers, right? On the 2D surface, you just need to know two numbers. So we just establish such the decal scale. Okay, so at this scale, we just try to read the position of the laser beam spots. Okay, so for that, we just need two scales, X and Y. But in our AFM, we give it a kind of different name. We call it vertical and lateral. So just do a brief introduction how this vertical and the lateral calculated. Okay, so we remove this one. So photo detector. So this kind of photo detector is just a photosensitive materials. So it's something like that. So this material is photosensitive. When a light shines on this surface, on these materials, if the wavelength of the light is correct, it can cause the photo chemistries, and it gives us out. It will emit out some electrons. So we do that in this way. So we put photosensitive materials here, and when the laser light shines on the surface, it will give out some electrons. And then we let the electrons go through a resistor. It can give us a voltage at this point. So by read this voltage, we know how large this current is, and then we know how many electrons it emits out from this photosensitive materials. So we establish a voltage is proportional to the light intensities on these materials. And this light intensity, we can say, is a light intensity at certain area times the laser spot area. So this voltage is proportional actually to the laser beam area. Okay, so that's how we establish such photodetector. And then we put 4 photodetectors in decal way. So we put 1, 2, 3, 4, and we call this 4. We call this 4 detectors, A, B, C, D. And then we measure the voltage of the photocurrent, VA, VB, VC, and VD. And then this VA, VB, VC, VD, we know is proportional to the area of laser spots on each detector. So this VA, they all follow this kind of relationship. So we calculate the so-called the vertical in such way. We calculate a vertical. We make it equals to the VA plus VB minus VC plus VD. And then we get this relationship in. Okay, let me put it up a little. Let me put it in. So this we define a vertical. It's VA plus VB minus VC plus VD. And we have this relationship. This V is proportional to the normalized intensity times the area. So this will be normalized intensity, which is the intensity of the laser beam per area times AA plus AB minus AC plus AD. Of course, there will be a coefficient there, so we just call this coefficient K. It's fine. So its coefficient is the resistors and the sensitivity. It's fine. It's just some coefficient. So this AA plus AB minus AC plus AD tells us what's the area of the laser beam, of the laser spots on each photodetectors. And this distance will tell us, okay, what's the center of the laser spots are. So this AA plus AB minus AC plus AD is the position. of laser spot on y direction, right? That's the goal we try to reach. But we found something annoying here. So this area difference is our goal, but the vertical value is proportional to the intensity per area and some coefficient. So let's just consider this situation. For example, we are doing the AFM, and you have an AFM tip, you have a surface, and this tip reflect the light to our photo beam. And then the laser position is somewhere here. And then we call this number, we wrap this number down. For example, with the VA equals to VB equals to 3 volts, and VC equals to VD is 1 volt. That's our situation. So we can calculate out the vertical. It's just simple, right? It's just 4 volts. But we have something wrong with our instrument, and we found our laser source got something wrong. And so the laser source is something wrong. It will decrease the laser intensity significantly. So the laser intensity is decreased. It's just this intensity per area decreased. But the laser position is defined by the deflection of the cantilever, which is related to the tip sample distance. This thing is still the same. So the laser spot would not move up or down, up and down, but only is changed is the intensity per area changed. So after broken, the laser signal reduced. For example, the VA equals to VB equals to 0.3 volts, and the VC plus VD still equals to 0.1 volts because the position does not change. So it will give you the vertical. It's 0.4 volts. So the vertical value changes, but we want to know, we need to make sure that here is the vertical. It's only related to the position of the laser spot. But in our case, the laser position does not move, but its value changes. So the problem is what? Is this. We want our vertical value to be independent of the laser intensity. So we need to normalize the vertical again. So that's why we, in our AFM ways, the real vertical we are using is we divided by the vertical value by a normalized way. So by how? So if we define the vertical is the VA plus VB minus VC plus VD divided by A, B, C, D sum, then all this coefficient and the intensity per area will be gone. Okay, so it only leaves out AA plus AB minus AC plus AD, and it will divided by A, B, C, D, which is a constant. So in such way, we can make the vertical only related to the area. It will be independent of the intensity and some coefficient. So for example, for this one, if we do that, our vertical value normalized vertical value, let me use the black. The normalized vertical value will be 4 divided by 8, which is 0.5. And after broken, the laser is reduced. The vertical value, normalized vertical value, will be 0.4 divided by 0.8 is still 0.5. Okay, so that's why when you watch the AFM series, you will find they're all divided by something. And this way is to normalize the thing. So from this small example, we can say, even if the laser spot is damaged, you can still get the normalized vertical value independent of the laser intensity. That's why we do this thing. Okay, and to watch the same, we add the value sum, and this value sum tells us the intensity of the ABCD. So we define sum equals to VA plus VB plus VC plus VD, which is proportional to intensity, normalized intensity, times a coefficient, times an area. And this area is proportional to the size of our laser. So this one is usually a constant. So the sum value is actually proportional to the intensity of the laser. So the laser is stronger, or more laser goes to the detector, the sum value will be higher. So this thing, actually the sum tells us how many lasers goes into our photo detector. So if the sum value is larger, means more laser goes into our detector. But we really looking at is the vertical and the lateral. But when you use the AFM, you all remember that the engineers told you, okay, the first step to adjust the laser beam is you need to maximize the sum value. Why? Okay, so when we look at this example, we say the sum value is 0.8 or 8. It does not affect the final vertical value because the vertical value is really we used. But still, we need to use the engineer still ask you to try to maximize the sum value, because the things here is we just use the normalized vertical, but this normalized vertical is measured from the voltage ABCD, and there is a measurement. There will always be a noise. So if your noise, when you consider the noise, we will say, okay, we may need larger vertical values. For example, if we have a noise, say our noise scale is positive minus 0.1 volts. So all our ABCD, they will have this 0.1 volts noise. So we will do a mathematical calculation here. It's what's the vertical? What the vertical will be the 6 positive minus 0.2 divided by 0.4 volts divided by 4 plus minus 0.4 and 8.4, right? So the final value will be 0.5, and the error, you can do this error translation way to in the statistic, it's about 0.05, something like that. But if our signal reduced to 0.3, and this thing will change, it's 0.4 plus minus 0.4, 0.8 plus minus 0.84, because our noise will not reduce, it will be a constant. So when you calculate this, you will say the normalized vertical will be 0.45 plus minus 0.5, right? Because our noise is same, but our signal is significantly reduced. So compare these two. We will say if the sum value is larger, it will give us better signal to noise ratio. So we say our signal stronger, so it will give us more accurate measurement results. So that's why the sum value will not affect the vertical or lateral, but it can improve the signal to noise ratio. So that's why in our adjustment, the engineer will ask you, okay, hey, we need to maximize the sum value at the beginning. Okay? Okay, that's the laser stuff. So we get the vertical, we get the horizontal, and this vertical and horizontal is proportional to the cantilever deflection. It's good. So we will use the vertical and the lateral to reach that, And the most important thing we will read is vertical, because the cantilever, the force we usually measure is the vertical direction, and this vertical direction force between tip and the sample will cause the bend of the cantilever in the vertical way. And such vertical deflection, such vertical bend will cause the movement of the laser position at the vertical way. That's why in AFM, the most important is the vertical. It gives us the force, okay? And the lateral usually tells us something in the lateral direction, which is friction, okay? So when you read friction, you are talking about the lateral, but in most of our AFM, we are studying the force at the vertical way, okay? So the vertical, in most AFM, it will just cause the AFM signal, okay? So that's the first problem conquered by the engineers. Yes, please.
At the beginning, you mentioned that the whole spot should cover all A, B, C, D on that area, right?
Yes.
But in the real situation on the AFM, usually we only have one laser spot, like the diagram underneath. Yeah. So if that portion, is it also A, B, C, D? The portion, the black one.
Yes, the ABCD. Okay.
But you mentioned there should be a big laser spot to cover all A, B, C, D regions.
Yes, quite good question. I have to admit, this diagram is wrong. This diagram is wrong. In truly way, is you mentioned, you want the laser beam to be large compared to the detector. If the situation is the detector is so large and the laser spot is so small, it will give some situation like this. Okay, so if our photo detector is so big and the laser spot is tiny, it's just here. So if our cantilever bend a little bit, all this laser spot will be where? Will be somewhere here. No. Will be somewhere here. So when the laser beam is at this position, we will say VA equals to VB will be a certain maximum value. And we say equals to VD equals to 0. And this vertical will be some maximum, right? Will be some maximum value. And when the laser beam is here or here, the vertical value will be the same. And then at this time, the vertical value does not represent the position of the laser beam, of the laser spot. So the real thing is we need to make sure our laser spot is something like this. It should be a large laser spot, or we should use quite a tiny detector. And in such way, the laser spot is moving up and down. It can make sure the vertical value is not always reaches maximum, which you are familiar with is 12 volts. Right? In AFM, you can say sometimes the vertical value or lateral value is 12 volts. That's the maximum. That's its limit. So the real thing is our laser spot compared to the detector is large. It's not like our diagram is small. No. But this diagram is just from the icon interface. And this way, they just use this laser spot to represent the center position of our laser beam. So it's just a diagram. It will just cause some confusion, but the real spot and the detector is something like this. It's large, it's small detector. Not like this, it's not large detector. Okay? And there's some details. Sometimes you will find out when you put the laser spots in the center of the detector, you will find that some value even dropped a little bit, because these 4 detectors are glued together, and the only 4 corners, they are photosensitive. Those glues, they are not photosensitive. So if the laser beam is centered in the detector, the photosensitive area actually decreased. So the sun value will decrease a little bit. Okay? But please keep in mind the laser beam compare the size of the laser beam and the detector is this, not like this. Okay? Okay, so we conquered the one engineer problem. We get the laser stuff done. So we control the distance. Finally, we converted into, we control the vertical value. And in the vertical value, we have some details. We maximize the sum value. We normalize the vertical and the lateral. We record the vertical and the lateral. That's the half of the story. And then the second half of the story we need to conquer is movement. Okay? So the physical scientist says, okay, you just drive the probe to move in X, Y direction and Z direction, that's it. But engineers will always ask how. Okay? So our goal, the 3 goals, the nanometer scale, the 3D and the in vivo. 3D and the in vivo is already done. It's already conquered. Only thing is the nanometer scale. You want to reach nanometer scale resolution, you actually need is the movement of X, Y, Z at the nanometer scale. So the same, the engineer problem here is we trying to find a way to drive the tip to move at X, Y, Z in nanometer scale. So we just try to find a certain way. So we consider our bag. How to do that? If you want to travel a long distance, you will use airplane or use the ship or even use spaceship. But if you want to travel at the nanometer scale, what's our the driver? We cannot use motor, right? We have so many Swiss companies that design those watches, and they put so many chips in the watches, and they can move the rotor of the 3 pins quite accurate. But again, that's all micro scales. We want to achieve the movement at the nanometer scale. So we need to find materials can move at the nanometer scale. So we again think about Okay, let's do the size stuff. You're all familiar with the quantum chemistry. You know the distance. You know some distance stuff. So the smallest molecule or atom is hydrogen, right? And the radius of the hydrogen is what? It's 52.6 picometers, right? I think I remember this number correctly. It's the Bohr or Schrödinger equation of. It gives us this distance. Okay, so that's the distance of the hydrogen. And now we want to move at the nanometer scale. We actually want to move in atom way. That's right. That's the goal. If you want to move in such distance, it's just moving this way. So we are actually talking about, we try to cause the movement in atom way. So think about a little bit. Our things are all established for the solid stuff. We all established that in the crystal way. And each crystal is a unit, we call it a crystal cell, right? The crystal cell, the size of each crystal cell, you're familiar with, for example, the gold, the copper, the sodium chloride is at the nanometer scale. So we want to move at the nanometer scale. So it's actually, we are talking about deformation of our crystal cell. And this deformation could be nanometer scale. So we are talking about movement at the nanometer scale. We are actually talking about, we deform a crystal cell at the nanometer scale. But we try to cause the deformation, it's fine, just press on it, it will just cause this deformation. But we want this deformation to be a controlled way. So that means you want a large drive signal. This large drive signal can be anything, can be force, can be electric, can be magnetic, can be anything. But this drive should be large. And then it causes a small deformation of your cell, of your crystal cell. That's our goal. Okay, what's this? If you want to use the force, the answer should be no, right? You cause a small deformation of your material, you need to apply small force. So the mechanical force will not be our candidate. We need another candidate. And finally, we have this thing, which is the piezo. Some materials in our natural world, its deformation can not only be caused by the force, it can also be caused by other stuff, such as electric field. And this thing has been developed, or has been discovered 2,000 years ago in Greek, right? So, and they call this thing piezoelectric. Sorry. And this piezoelectric is, people find out that if you apply a force on a certain material, sorry, let me write it down. If you add some mechanical force, it will cause the charge distribution change. And this thing, we call it piezoelectric effect. And sometimes they found, okay, it has a converse effect. Means if you apply an electric field, it can cause a deformation. This we call it a converse piezoelectric field effect. I'm sorry, converse piezoelectric effect. And this thing we can prove in thermodynamics they are the same. So that's not our goal here. Is we try to say this kind of they say why we have this piezoelectric effect or converse piezoelectric effect. We go back into the crystal cells. In crystal cells, they are not just a construct. They are just made up by the atoms. And these atoms or ions, we know they are all charges. For example, the things you are so familiar with peroxide. Okay, so it's calcium, and there will be a titanium in the center, and it will be oxygen in the face. And the titanium and the oxygen, they are all charges. Titanium are 4 charges, and the oxygen are negative 2 charges. And if you apply a force to press on this cell, you actually change the relative position of the titanium and the oxygen. In the macro scale, you cause a charge distribution. And if you apply an electric field on this crystal, the titanium and the oxygen will move in opposite way, right? The titanium will just follow, it will follow the electric field, and the oxygen will just move in the opposite way. As such, you change the relative position of titanium and oxygen, which at micrometer scale is a deformation of the crystal. So if our crystal cell are ions, and there are some the unsymmetric thin stuff, we will have this piezo effect or converse piezoelectric effect. Okay, so that's the main principle. And from this principle is we can say the electric field is something we can apply, which is voltage, but the deformation is small because it's the deformation at the crystal scale, at the crystal unit scale. So we finally reached, you apply a large voltage to achieve a deformation at nanometer scale. That's the goal we want. That's the thing we want for the AFM. We want to move our tip or sample at XYZ at the nanometer scale. We use the piezo as the driver. Okay, so this piezo driver, we can establish this relationship here is the deformation. Of course, this deformation here will be string in the physics is string, but it's fine. We call it deformation. This deformation is proportional to the electric field we applied. In the engineers, we put it this way. We put the piezo effect materials, usually it's a ceramic. We put it between 2 electrodes, and we apply voltage at these 2 electrodes. We achieve an electric field between the 2 electrodes. And then we apply a voltage, we establish an electric field, and according to this equation, we cause the deformation of the ceramic. And this deformation in macro scale, we call it, it's a movement, right? So that's the how we achieve the nanometer scale movement. We use the piezoelectric. Okay, so that's we finish this slide. We will just be close at in the morning. But how? There are many ways to achieve this movement, and we can, for example, For example, we can make a plate. And make a plate, we just hold the sample onto the plate. And then this plate, we can apply a voltage. And by apply a voltage on the plate, we can cause the expansion of the plate due to the piezoelectric effect. And so after the plate expanded, it will be something like this, right? So after voltage, and then the sample is still holding onto the seat. So we can say the center of the sample cause a movement, right? That's a way to do this kind of, to achieve this movement. But in such way, you need so many plates. But it's fine, it's also one way to establish AFM. And that's you will heard is about the planar, the planar AFM. In that way, the sample will just move in the plane. That's a planar AFM, which is some of you guys are using is the bioscope resolve or faster scale. They are using this one. But for but for this kind of thing, you will say, okay, you need some piezo ceramics. They are separated. You need a plate here, and you will also need a plate here, right? You need to also move in the y direction. So the planar movement, it will just cause separate x, y, and z. And in the most traditional way, we will make the piezos as a tube. And in such way, you can make all this x, y, z movement assembled in a unit. This is a model of our piezo tube. Or in the AFM textbook, they call it tubular piezo scanner. Okay, so they make them in this way. They put the piezo ceramic as a tube, and we talking about x and y. Okay, so they put the electrodes in the opposite way. So we have a x, and in its opposite, there will be an x negative. And then we can apply voltage independently for x and x negative. And usually we will apply voltage for x and x negative in a just opposite voltage. For example, for the x, we will apply such triangular shaped voltage, but it will increase first and then decrease, increase, decrease, increase, decrease. But at the same time, we will apply voltage on the x negative, but in opposite way. It will decrease first and then increase. So let's say how it will happen in this setup. So we have x negative and x positive, and then it's band together. By apply a positive voltage on the x side will expand. So it will get longer. But at the same time, we will apply a negative voltage on the x negative. So the x negative will shrink. But again, they are bonded together. So let's talk about if we put a tip, FM tip, at the center of the x and the x negative, you will say here x is in the center, but in this direction it will move, right? It's just like a ball, it will move. So, and then you move it back and forth. you make the X latitude expanded and the X latitude shrink. The tip will go to here. So as such, you apply voltage on X and X latitude, it can cause the tip to move like a ball in the X direction. And at the same time, you can apply voltage on the Y. It can also make a movement in the Y direction. As such, you can cause the tip or the sample to move in the XY surface. That's the tubular scanner. Okay. And the tubular scanner will give us an advantage that the whole thing is a unit. It can make it more robust. But of course, it can cause a disadvantage. You can say its movement, its trajectory is a ball. It's not like our planar movement. It's not a plan. So that's why you guys do the AFM image on icon or multi-mode. When you do a large area scan, you will say the result is kind of like a ball because the tip movement is a ball movement. Okay, so that's just the way to get the piezo movement done. And for Z is quite simple. So you apply voltage on the Z, it will expand at the Z direction. Then you can get the tip up and some movement. So finally, we get the engineer problems done. So we make them together to say how the AFM works.
I have a question.
Yes, please.
How rigid of the tube? Because the force is quite small.
Mm-hmm.
If they make it as tube, if there's removing some XY X direction, if the force is small,
Mm-hmm.
then it cannot overcome the Y axle deformation of the rigid. But if it's large, it's difficult to control. How to make such kind of you can control, but it can still keep it rigid or keep it constant of the tube. Because if a panel, if only one direction, it's easier. If one direction is easier, we just we are concerned about the extension or elongation of it.
Yes.
But, if you make it as a circle, how to overcome such kind of another axle limitation?
You mean you move
Just like a balloon.
Yeah.
If you comfort one and the other will elongate.
Yes. That's a good question. When we do this step, we get it done in the calibration, and we call this crosstalk between the XY movement and the Z movement. For example, so this is a tube movement, and we want to move it in the XY direction. It actually is something like this, and something like this. So when it's really moved, it will something like this. So the XY movement, it will be a Z movement in the company. So that's why you will get out in the image, you will also say Z movement. And to compensate that, we will do that in the calibration. But no matter how, you will say the Z movement accomplished with the XY. But in principle way, we do that in this. So that's what I'm coming to. So in the AFM principle, we control the distance as a constant. And this control is only by movement at the Z direction. So in AFM, we separate X, Y, and Z. In the AFM, if you remember something, when you're doing the parameters, you actually define two things. One is your scan. You define your scan size, define your scan rate, all this stuff. You are actually defined X, Y. So how the AFM works, we are thinking about something like this. For example, I have a cell phone here. I have a brush here. I want to know the distance since we want to know the height difference between the brush and the cell phone. What we will do? We will define x, y area first, and then we net our tip to travel on this surface. So the AFM will do this way. We define x, y by me. I tell the probe to move at a certain area, and the size of this area defined by me. The speed of this tip on this area defined by me. So I define a region of interest first, and then what I really measured is the movement at the z direction. So the AFM will be, we define x, y. By defining this x, y, we actually defined what's the size of this area, what's the shape of this area, how fast the movement at this area. And by this, I define a region of x, y. And then that's all x, y. And then I will keep monitor the vertical value. And to count, our goal is to make the vertical value equals to a certain constant. By how? By move the z. To move the z at this, to achieve the tip movement at the z direction. So this one, we establish a loop. So in the AFM, we will just keep watching at the vertical value. If the vertical value increase, means the tip sample force increased. So the tip is too close to the sample. I need to move up it a little bit. If the vertical value decreased, means the force is so small. I need to press down the tip to make the vertical value as a constant. So the goal here is we use the vertical value to control the z movement. Okay, so but our tip will also move in the xy direction. So we find something like this. We define an xy area. And at this area, we will just do one thing. To get the tip movement, to make sure the vertical is a constant. So we actually record is the z position at each xy point. So in this way, the xy is just a scale or in mathematics, it's a matrix we defined. And then our matrix, the unit we put in this matrix is the z position. And then we put each z position at each xy position. We record the z position at each xy point here, and then we make finally this kind of matrix. And the matrix unit is the z position. And so we separate x, y, and z. The z is controlled by vertical. The xy is controlled by me. I predefine the xy. And then I establish this matrix. And I record the z position at each time. And I put the z position inside this matrix. And finally, in AFM, if you define a color for each different z position, you get a color scale, and then it gives you a map. That's the thing you finally get out. So in principle, it's just a matrix. Our result is just a matrix. So back to your question, it's of course in your xy movement, it will cause the z position difference but it's fine because it's separated. And this Z position movement is already controlled by the vertical. So if your X, Y direction movement will cause some Z movement, it will all conquered by this, the vertical things. So we all get all these things back into the final results. And for that, if we want to do some, if we want to remove this ball effect, we just do that in the post analysis. But in the movement, it's separated, then it's okay. Okay, so after that, we can say how this AFM works. You define X, Y. Yes?
Do you mean that the set movement is actually we just monitor the height, the distance between the tip and your surface, and if the surface changes, the height changes, we record that movement and we feed back to our seat motor and adjust the height of the tip. Is that this way?
Yes.
So if there is, so it seems that we just detect the height changes first. So if there any delay to the seat movement?
Yes, that's the problem. It will give you artifact.
Yeah, okay.
Yes, it will give you artifact. That's why the XY cannot be too fast. Then it will cause you defect. Means the Z direction movement cannot catch the XY movement. So when we're talking about speed, we are actually talking about the XY movement. That the XY movement should be small. They should wait for our tip to move in the Z direction. Yes.
So if the XY speed is slow enough, we can avoid the artifact.
Yes, we can avoid artifact. So the engineer will always tell you, you sacrifice your time to get a good image. Yeah. Yes. So the final way is, and in all our next days, the discussion session is just the main here is how we make the vertical constant to control the Z movement, how we adjust the XY movement to give us better Z movement. That's the next session. Okay. Okay, I think that's all for the morning session, and thank you.
Hello, welcome back. Before the beginning of this afternoon session, I would like to share 2 points. First is for the training material, the SIG book. Because in the early stage, we want to limit the size of this training class down to maybe 25 personnel. But later we noticed that due to the overwhelming registration, so we send out just 2 batches of this training material, training book. The second batch will arrive this afternoon, and we just checked the FedEx. It is being delivered now. So for the second batch, we have around 60 books, so should be enough. So this is first point. For the second, because our training is a 5 days course. In our past trainings in mainland, usually we request that everyone should go through the whole 5 days per courses, and we do have a quiz on Friday in the afternoon. And but now, because the large size of this training class, I'd like to know how many of us will go through the whole 5-day training. Okay. It's around 20. Okay. We do hope that more people can finish all these 5 days, because we have different topics for different time, and it's basically a stepping up procedure. Okay. So for those who will finish this 5-day class, we will make sure that you have one handbook because it's very important. And if some of you haven't been signed on, please finish the yes. Okay. Oh, after the classroom session, before the hands-on session, we will take a group photo.
Okay, let's continue. Okay, let's first give a brief review about our morning session on the AFM principle. So, our principle is for the AFM, is the scanning probe. Yeah, thank you. For the morning session, we discussed the principle of the scanning probe microscopy. It's about how to get topography of our surface. So let's make a brief summary here. So for SPM, for scanning probe microscopy, we use a probe to scan the surface to get the topography we want. So we need to define our region of interest. To do that is actually we define the XY scan area. So this step we will define many things. For example, the scan size. We define the scan size, we define the rate, blah, blah, blah stuff. And during the movement of the tip, during the scanning, we want to control one thing is the probe keep in touch of the surface. And in principle way is we need to make the distance between tip and the sample is a constant. And to achieve that, we do this kind of movement is we define a certain physical value, and this one is a function of distance between tip and the sample, and we make this physical value to be a constant. So for this physical value, the first physical function, the first physical value or the first function we found is the tunneling current. And we want to make sure the tunneling current is a constant. And the second physical value we found is the force between tip and the sample. And we want to make sure this one is also a constant. So, and this the force between tip and sample, we use a way we fix our tip on a cantilever. So this force between tip and sample, we convert it into the deflection of cantilever. But again, we calculate that the force is at about nanonewton to piconewton. And this deflection is picometer to nanometer. So it's also a small value. It's still not large enough for us to measure directly. So we use a laser beam to enlarge the deflection. So we convert the deflection into vertical value. And so the tunneling current and all the vertical value, we want to make it to be a constant. By how? By changing the tip at z direction. So we move the tip up and down to make sure its vertical or tunneling current is a constant. And this tunneling current is the so-called STM. And the vertical or the deflection stuff is the so-called atomic force, AFM. And this one, we want them to make a constant. And so by adjusting the Z movement. So during our scan at a defined area, defined XY surface, we move the tip up and down, up and down, up and down. And then we record the Z position at each point. And finally, it gives us a map of Z position in the scan area we define. That's the topography, right? That's the whole idea about our AFM. So the XY is defined by me, I define an area. And then I use the Z to control the tip moving up and down, so the current or the vertical is a constant. That's the whole idea, right? That's the AFM whole idea. So let's go over some details. So the first details is about the XY movement. The AFM movement in the XY direction will also make a small change. And we'll also make them a little bit different. Usually, we will let the probe to have a fast direction movement. So for example, if we want to scan, this kind of area, how we do that? Usually we will make this kind of movement that we want our probe to scan the whole area. So we move this kind of way. So we let the probe from here and do this zigzag movement to get the whole area, to achieve the whole area scan. So, and in this way, we will have a horizontal line, and then in the vertical direction, in this y direction, we will have many scan lines, and then this scan lines will patch a surface, will patch our scan area. So how do we achieve this kind of zigzag movement, or we call it raster scanning? How we achieve that? We can just separate that into two ways. One is we let them back and forth in this x direction, and we make them scan quite fast. And then in the y direction, we also make it to do the scanning. But in the y direction, we move it scan quite slow. So with this two speed, The X speed is large, the Y speed is slow, it combines together is this kind of raster scanning. So in the AFM, we usually will make a definition. We will have a fast scanning direction and a slow scanning direction. And the fast scanning direction in our slides here is we use the X direction as the fast scanning. So the fast scanning is just the scanning back and forth quite fast. And in the Y direction, we make it quite slow. And this speed, because we are using the piezoelectric to control the movement, so actually we are just controlling the rate of change of our voltage. So that's how we achieve this fast scanning and the slow scanning. And combine them together, we will get this raster scanning. So for some AFM applications, some researchers just want to do a line scanning. So in the line scanning way, it's just to make the slow scanning equals to 0. As such, the piezo or the scanning does not move in the right direction, so it will keep back and forth on a line. So in your when you're using the icon or multimode, you can say a parameter called disable XY scanning, the disable slow scanning. That's what that means, just to achieve a line scanning. Okay. So from that we will continue. So for AFM, since it's doing this raster scanning, so we can say in this way. So in each scan line, we will have just doing a line scanning. And then for this whole image, it's just like so many scan lines, and then it parallelizes it, putting together to give us a frame. So we can define this way. In each scan lines, we can define how many data points we want to capture along these scan lines. So we call this samples per line. For example, the normally used is 256. That's what we are always using. And then to make the whole frame, we need how many lines? We call this number lines. Okay, with that, we can define a what? A blank matrix. And this matrix in the horizontal line, in the rows, we are just samples per line. And the columns is lines. So this, we define an empty matrix, and then at each data point, we record the Z movement. And the Z movement, how to achieve this Z movement is we actually apply a Z voltage. Apply Z voltage, we will make the piezo to move up and down as such to drag the tip or the sample move up and down, up and down. So we record the Z voltage, and then we get the Z voltage, we capture what's the position in the XY at this data points, and then we put the Z voltage inside this matrix. So it's Z voltage 1, Z voltage 2, blah, blah, blah. And finally, once the tip from this points ended at this points, the Z voltage will fill the whole matrix. And then finally, you get is a matrix of the Z voltage. And then we do some calibration. We transfer the Z voltage into the deformation of the piezo or the height. And then we get a matrix of height. And so, and then we will just make a color mapping. At different height, we give a different color. And then you will get a map. And this map is what you are looking at. It's the so-called height image. Okay, so it's actually the AFM raw data is just a series of numbers. In its raw unit is voltage, and after calibration, you actually get a series number of height. And then with the height, from our defined samples per line and the lines, we will put these numbers in this matrix, defined by these two numbers. And then you will get a map. And of course, you will ask, okay, what's the size of this map? You will define by this XY scan size. So we can say here is the AFM, the region of interest you are scanning is you define the frame of this matrix, and then the AFM will do this kind of Z direction movement, use the vertical or autonomy current to control the Z movement. We capture the Z voltage and put these numbers of the Z voltage inside this matrix. You get a height topography. So when you look at the raw data, you will see just a series of numbers, and these numbers are just matrix components. You just need to know the size, the frame of the matrix, and then put the numbers in. You get the image. That's our AFM topography. Okay, so that's how we get that from this movement. Okay, so after that you can understand how what the parameters we are adjusting is just two parts. You define XY, and you adjust your numbers to make this control to achieve your goal, right? Your goal is the current or the vertical as a constant by adjusting the Z movement. So the AFM parameters are two groups. One is the scan, and in the scan you will define scan size, scan rate, blah 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 stuff. And in other panel is the feedback. You will define your set point, you will define your gain. So that's the details we will continue. Okay. So let's have more details about our piezo. The piezo, as we said, the piezo is our scanner is based on piezo electric properties, and in our ideal way, we want our deformation to be linear with the electric field we applied, but in the physical ways, we don't always have the linearized the relationship. So we will say the deformation and the electric field may not be linear. So for a non-linear relationship, how we do that? The most common way we use Taylor expansion or Taylor equation to get it out. So we will define the relationship between the electric field and the deformation. It's a nonlinear relationship, it doesn't matter. We use the Taylor equation to do that. So you will get the first order term, second order term, third order term, blah, 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 keep going. And from that, we can get a precise relationship between electric field and the deformation. We want deformation, right? The electric field is the voltage we applied, but we really want to know is the deformation because we want to know the height value in nanometers, not in volts. So this one, we call it calibration equation. So in the AFM, you really need to apply a voltage to cause the Z movement, but you really want to know is how many meters does the piezo move in the Z direction. So it will involve a calibration here. Since it's non-linearized, so we will have lots of this kind of Taylor coefficients. That's what we are doing in the calibration. So there's some of you are multimode users, you will say, okay, you need to calibrate these numbers at different Z heights. The reason is the relationship is non-linearized. So this one is our so-called calibration equation, and after that you don't need to really we don't really need to know this one, but we really need to know after the calibration coefficients, we can directly get the height. Okay, so that's about its non-linearity. Okay, the second thing, another thing we need to focus on is the creep. As we explained, we are using the piezoelectric effect to drive the piezo to drive the sample or tip to move. What we are driving, we are just apply a voltage, and then we want the crystal to deform. That's the that's the converse piezoelectric effect. So the voltage we are applied is just an electric field. So we can tell the voltage change. It's just we can change the voltage quite fast. The speed is what? It's the light. It's the speed of light. But no, we don't. We just remove here. This is a piezo. You apply a voltage and you want to change you want to cause the deformation of our piezo. The voltage applied, you can change the voltage, you can apply voltage, you can convert the direction of the voltage quite easily in the software because it's changing at the speed of light. But we are really, but what's the really movement is the crystal here. And to cause the deformation of the crystal, it cannot move following the speed of light because it's atomic, it's the movement at atomic scales. So the movement, so the deformation is quite slower than the voltage change. So that means if you want to change the tip or sample position, you change the scan size, you change the scan area, you are actually changing a voltage. And you want to, at that point, you want your tip to move to just following your voltage change. But sometimes they cannot change as fast as we just change the voltage, and then you can see this kind of distortion at the image. And we call this phenomenon creep. Means the piezo is moving just like a worm, but our voltage is changed so fast. So you change the size of you change the scan area. In your software, it will consider, okay, the piezo has changed its movement, but no, the crystal cannot deform as fast as your voltage, and you will see some distortion at the image. That's the creep, and it's quite common, especially in multi-mode system. Okay, so This kind of creep gives us a problem here. Is the x y movement cannot be as accurate as we want. So okay, so we can take
So the chain book has arrived. We have 14. So those who don't have, if there are more than 14 people, then we'll give priority to those who will attend all 5 days training. So, hands up. Guys, Okay, you 1, 2, 3. We are running out of hard copy. So, will you attend the 5 days change class? Yes, we send out some copy. If you need, because those are printed in mainland China. Okay. This is
okay. So let's consider this this situation. So we have a starting point A and end point B. So we consider this situation is we say change tip position or sample position, or we change scan size. We are just make this as an example. We are trying to move our tip or the sample from point A to point B. And so we know the position of each point. So how we get the position movement, or how we achieve this kind of movement? So let's think about this way. So we know the position A, we know the position of B, and then we can get the distance between B to A, right? And from the distance between B to A, we have the calibration equation. We have the calibration equation from the distance from B to A. We will calculate to change the position from A to B. We need to change how many voltages on that, and then you apply this voltage, and then the piezo will goes to the position B, and due to the creep, and due to this creep, we know, okay, the movement from A to B will be slower than you apply a voltage, and then we get the creep. Okay, so that's the same. We may now want this. We apply a voltage. We want the tip to go from A to B quite fast, as soon as it can. So let's consider how we do that in in the race. So you have a starting point A, you have an end point B. If you are just on a racing, you are just running or just driving cars, how will you do that? You do not travel from A to B at a constant speed. That's not our strategy. We want us to travel from A to B as fast as we can. How will you define your strategy? You will just speed up quite fast at the beginning, and then when you try to almost reach B, you will reduce your speed. That's our strategy. Okay, that we will not use a constant speed. But for this kind of strategy means the velocity we increase first and then decrease at the end, and then make us to reach B points. That's our strategy. How we apply this strategy is we need to know the position of the B. That means we need to look at our end point, and when we get closer to the end point, we need to slow down. That's our strategy. So to apply this strategy, it means we need to know the location. We need to know where we are from the A to B movement. So, but when we are looking at the piezo, when we're looking at our scanner, the piezo ceramics, does it know how many meters it deforms? No. You only apply a voltage and then it deforms. How many nanometers it deforms? We do not know. That's the point here. So for this kind of thing, to apply this strategy, we need to know the position, and then we can know the distance between us and the endpoint, between us and the B. So we need to know the position of ourselves. So for the scanner, we can have a different strategy. We have a piezo here, and we want to know its position. We gave it a small sensor. The function of this sensor is to read out the piezo deformation. So usually this kind of sensor can be a capacitor or resistor, anything. Its usage is to read the piezo movement, is to read the piezo deformation. So as such, we can, with the sensor's help, we can apply our strategy. So we will, from the sensor readout, it will give us the position. From the position, we can calculate the difference between the current position to the end. And from this, you can use this to define the strategy of your velocity. And then it will also cause the change of the sensor. So with the help of sensor, we can control the movement of the piezo from points to points much faster. So this kind of strategy, we call it closed loop. And with the help of the closed loop, we can conquer such artifacts. So usually when you are working with icon, you don't say this kind of artifacts too much. So this one is just this is just one property to conquer this kind of creep. So, but the sacrifice or the cost we are causing is we need to add a sensor on the piezo. So when you are working with icon, bioscope resolve or dimension plus scan, you can say, okay, there is a parameter cost. Are you going to use the closed loop? So with the closed loop, you can use the sensor to control the piezo movement. Okay, It's not just at the end, we can keep going. So the scanner, we have a scanner, we have the X, Y direction, it has sensors. The Z piezo also have a sensor. We call this sensor Z sensor or height sensor. Okay, so during our principle, we want the vertical value to be a constant, and then we will apply a voltage on the piezo. And once we apply a voltage on the piezo, we can record down the voltage we applied to put these values in this matrix, and after the calibration, it gives us a height. That's the height you say in multimode, and the same height you can say in icon. And at the same time, you apply a voltage on the scanner, so the piezo will move up and down. Once the piezo move up and down, the Z sensor will record it's moving up and down. So we will also put the Z sensor value inside this matrix again. This is the Z sensor readout. And this matrix, we call it height sensor. So that's why that's when you doing the AFM on the icon or fast sky. The topography channel name is height sensor because its original data is the Z sensor readout. So let's make a brief comparison here. So the height is the voltage we applied on the piezo, and from the calibration equation, we can tell what's the movement in the Z direction according to this Z voltage. And what's the real movement of your piezo? It can be read from the Z sensor. So of course, if your calibration is accurate, your calibration equation is correct, the height and height sensor value will be the same if your calibration is correct. But in the electrical loops, we can consider the height. You actually capture height first, and then you get the height sensor. The logic how it works, you get a vertical change, you will cause a Z voltage change, and then the Z voltage will give you the height channel. After the Z voltage applied on the piezo, the sensor record its movement, and then you get the height sensor. Of course.
So is it that means the sensor is just the adjustment of your recording?
No, the sensor is it's just the same as the weight, but it's just two ways to get the topography. The height is from the voltage you applied, and the sensor is just the readout of the Z piezo movement.
So now you have the two heights of it. One
Yes.
is from the voltage of it.
One is from the
Yes,
voltage.
the theoretical value.
Yes.
And then the sensor, you get the actual value. Is it?
Yes, and you get also another value from the sensor.
But finally, you're just using the sensor value, not the theoretical value. Or you combine both of them.
You can use any of them. You can use one of them. Each of them is fine. But the point is the height value requires you an accurate calibration, because the height value is depends on your calibration equation. If this equation is some defect, then there will be maybe some we don't say the wrong, it's just some change on the coefficient, and it can cause some error in the height in nanometers. So after accurate calibration, these two are the same. These two are the same. Okay, but yes.
So those two values are reflected by the trace and retrace
Yes.
on the graph.
Yes. Yeah. So for icon or fast scan or bioscope resolve, you can use either of them if you do the calibration correct. Yes. And for multi-mode, we don't use the sensor. We don't have the sensor. We only have piezo. So the multi-mode only have height channel. Multi-mode does not have the height sensor channel. Okay. In traditional way, in the classic AFM way, they would say they would say the height channel is a little bit more sensitive than the height sensor, or they would say that the Z sensor will cause a slightly higher noise than the height itself, because you just add another electrical device here. You add a device, you just increase the noise a little bit. So that's why for the high resolution imaging, multi-mode could perform slightly better than the icon. That's the reason, because it does not have sensor. The noise is slightly lower.
But how do you do calibration if you don't have the sensor?
Okay, so once we do a calibration, we just want to establish this relationship. The voltage is we applied, and the deformation is what we are trying to measure. So for calibration, is you get a sample with long distance. For example, you have a trench, you know the depth, and then you use the AFM to scan this trench, and then you know that this trench, for example, our sample is 180 nanometers. That's the depth of the trench. So this one is defined as 180, and we capture an image, and we know how many voltage we need to apply to get this trench, and then you get a voltage here, and you put the numbers in, you get the coefficient for this equation. So that's the calibration. That's we're doing in a multi-mode. You need to do the calibration using that standard sample. Okay. Okay, so that's the difference, the so-called height sensor and height. Okay, so any of them is fine, but for the icon users, they prefer they use height sensor, much more common, because it does not require a frequent calibration. Okay, so for the height sensor, is we control this way. We do not use the Z sensor to control the movement of the Z piezo. The Z piezo movement is controlled by vertical. That's why we do not use the Z closed loop when we do the imaging. But for icon or fast scan or resolve, we usually open the closed loop. This closed loop means XY direction. Why? Because XY is defined by us. We want our movement to follow my desire. So we always open the Z closed, we always open the XY closed loop. Okay? So in the hands-on session, you can play around with this kind of XY closed loop. Okay? So that's about the creep, and to conquer the creep, we define the closed loop. The closed loop requires a sensor, and that's why we have a sensor for icon, fast scan, and the resolve. And for multi-mode, we don't have the sensor for higher resolution. Okay, and the hysteresis is just due to the friction force. It's going back and forth. It has such this kind of loop. So for the scanning, we have a defined scan area, and then we use our probe to move back and forth. Okay, and when we're looking at this, this kind of images, we will say all this from left to right, we call that trace. And it's moving back from right to left, we call it retrace. All the trace lines, they are parallel. All the retrace lines, they are also parallel. But the trace and the retrace itself, they are not completely parallel. So finally, to form an image, we will only use all trace lines or retrace lines. And that's what you are using in the AFM images. You can choose, you are using retrace or you are using trace. Either of them is okay. But in this community, we commonly use retrace. And we will say the reason in the fifth step when we discuss KPFM and the EFM. But in your topography image, either of them is okay. And you can of course, you can choose. And this trace and the retrace movement for piezo, it has some defects. And this defects is called the hysteresis. And this hysteresis is just caused by the piezo effects. So this hysteresis will just give us some artifacts during the scanning. Of course, to conquer that, we will do a calibration and to using this kind of corrected nonlinear waveform. That's all calibrated during the AFM. Okay, and the last thing about the piezo is the piezo it has the aging effect. Its aging effect means its calibration equation will change as time. So the calibration coefficient is not a constant. It will change due to the aging. So that's why the engineers or the staff will tell you, okay, we need to provide the maintenance for the AFM. The main maintenance is we calibrate your AFM annually, especially for multimode, because it will affect the height. For the height sensor, is another advantage is its aging effect is quite tiny. So for icon, maybe you don't need to, maybe you haven't do the calibration for years. You will find out that the number is still okay, because the sensor, the height sensor value is quite stable. Its coefficient would not change due to the aging. Okay, so that's for the multimode. We need to calibrate annually. Every year we do the calibration. Icon is okay. Okay, so and then we need to another important thing is we need to protect against the acoustic noise. So let's think about let's look at this AFM image. For example, we have a step, okay? We have the step, and from our topography image, from our principle, we want the probe to follow the step, and our movement, the tip movement, will give us the topography of our surface. So from the tip, from A points to the B point to the B points, and it will move up and down. It gives you such image. Okay? So if we consider a situation when the probe reaches here and there is some vibration in the environment, somebody is just tap on your AFM, somebody is just stride and comes in to make large noise. Any noise, it causes the vibration of the sample. And usually when it causes a vibration of sample, it will change the position of the sample at the Z direction. For example, if the sample is jumping up, so your sample goes to here. Your sample lift up. So, but
look at the red tip, it's also stay on the blue line, but the sample is already larger. So the sample tip force will of course increase. And the force changes. What do we need to do? We need to change the Z voltage. As such, the tip can trap the surface again. So let's consider the situation. So the tip move here and lift up at this point. Suddenly the sample moving up. Our tip has also to moving up. So it will move this way. And then follow the surface again. So this one, this step change is due to the topography, but this step change is by what? It's due to the vibration. So, and your final topography will be this kind of two-step images rather than this one-step imaging. So this second step is the artifact. And this is, of course, caused by the vibration. So in the AFM, if you have any vibration, if you change any slightly change of your sample or tip position, it can be recorded in our topography images. And of course, this is artifacts. We don't want these artifacts. So by that, we have to make sure our sample is settled, is stable. It does not move up and down. So we need the protection against the acoustic noise. That's why you will have an isolation table. You use the argon or nitrogen float your AFM up, and then you need to put it in a large acoustic hood. That's the reason. Because we want our sample to be stable. And if the sample is stable, you get the image of your sample rather than its movement. Okay? So that's the reason we have this production. Okay, so finally we get the AFM principle, the AFM principles. We get how the tip is moving x, y direction, and we record its z direction, and then we will say how it really moves. So this thing is the so-called Lennard-Jones potential. It's about a primary model between the tip sample interactions. And this thing you are so familiar with because it's almost the same as the van der Waals force. So it tells us when the tip is get close to the sample, it has two basic force. One is the attractive force, and the second is the repulsion force. And the total force between tip and sample is almost the same as this of this red lines. So this line gives us a basic relationship between force and distance. We want to control our final goal is the distance is a constant by control the force as a constant. So the different AFM imaging modes just gives us, okay, what's your force is. For the most basic imaging modes is the contact mode. We're mainly at the repulsion range, and for the tapping mode or the so-called non-contact mode, we are imaging at the attractive force. So we will go through the details later. Okay, so first let's talk about the contact mode as our starting point. Okay, so okay, so let's say how our AFM works in the contact mode. So let's again we have a sample. it's a bump, okay? And we defined our AFM probe from A move to B. That's our X, Y direction movement. It's defined by me. So I defined the tip has to move from A to B. And during this movement, we need to guarantee one thing: is the vertical is a constant. Okay, so let's say how it moves. So our goal is the vertical value. It should be a constant. Okay, so we record the vertical here, and we make this vertical to be a constant, and we call this constant value set point. So the vertical should always stay at set point, okay? So from A to B during the movement, so we define another 4 points here. So this one is C, this one is D, this one is E, this one is F. So let's look at from A to C first. From A to C, our surface is completely flat. It's completely flat. So from A to C is the same height. Our goal is the vertical should be at a constant value from A to C. So our goal is A to C should be a flat. Does not change. How we guarantee that? Is our tip Z voltage should be a constant value, right? You do not change the tip position. From A to C, you stay at the same height to do the movement. So the Z voltage will be a constant value. Okay? Once we reach the tip, reach the C position, what happens? The sample is a bump. So when the tip reaches the C position, the sample itself increases, is tall at the C position. So the tip at C position, but the sample is already at the D position. So the force between at this C point will increase immediately. And this force increase will cause the vertical value increase immediately, right? So right now our vertical value is already at C position. And then our goal, the vertical should be at a constant, but the vertical changes. What do we do? From this change, we know the tip is get too close to the surface. So we need to drag tip up. So from this point, our tip should move up. How we move up our tip? We apply higher voltage on this point. So we would increase the Z voltage. When we apply a larger Z voltage, the tip will goes up, and when the tip goes up, the force at this position will of course slightly decrease. The force decrease for a speed is almost the same as our Z voltage increase speed. When it will stop, once the vertical dropped to the set point, it will not change anymore because the goal is the vertical should be stay at set point. So once the vertical dropped to set point, the Z voltage should not change anymore. So the Z voltage will be here. And then our tip is always moving from A to B. That's defined by the XY direction, by my desire. So the tip will be somewhere here, right? And then it will go on move on the DE plane, on the DE line. So this line is a plane again. So our goal is vertical should be at a constant here. How we control is a constant. The Z voltage should also be a constant value. Okay, and then once the tip reach the E position, when the tip goes to the E position, the sample dropped again. It's a bump. It drops again. So at this point, the sample is already onto the F, but your tip is on the E position. So the force between tip and the sample will reduce significantly. So the vertical value will drop again. And then at this point, what our goal? The vertical should be a constant, but the vertical is smaller than the set point. So what we'll do? We need to reduce the Z voltage to let the tip goes down to the surface. So we reduce the Z voltage. At the same time, the vertical will increase until it reaches set point again, and then the tip will be somewhere here. And tip will not stop, it will go to the B point. So it should be a constant at this trajectory. To make this trajectory, our Z voltage should be at a constant. And finally, that's point A, that's point B. And from this movement, we get this Z voltage change. And from the Z voltage change, we apply a calibration. We will get the height from A to B. That's our AFM imaging. Or we get that from the height sensor. That's our AFM imaging. Okay, that's the so-called contact mode. It's easy, just to make our vertical to be at a constant. We call this constant. Okay, so from these images, we can tell quite clearly that our sample is a bump, and this angle is almost 90 degrees. But the final image we get is something else. It does not look exactly the same as our images. And what caused this problem? It's here. It's here. So for here, what our goal wants, we have a bump, we have a height change from C to D. We want our tip to jump from C to D as fast as it can. So this kind of movement is too slow. So this one is caused by Z movement is slow. But we need to keep in mind we have some of you asked in the morning. We are moving in the XY direction. If we move in XY direction from A to B as slow as we can, it gives us enough time to do this Z movement. We would not have such artifacts. So this one is also caused by XY is too fast. So for ideal AFM imaging, if we move in Z direction as fast as we can, and in XY direction as slow as we can guarantee the final image is exactly the same as our true topography, right? That's the contact mode settings. Okay, so from this we get the AFM images, and in the contact mode, if you remember, this one is so-called our height and or height sensor, and this channel we call that in our imaging deflection arrow, right? That's the two images we get. We will discuss the deflection error or how it works tomorrow about the PID gain stuff, but that's the AFM images. Okay? So for the contact mode, it's just a basic image mode because it's just the same. It's quite straightforward to think about. It's quite straightforward to achieve in engineers. We just need to record vertical and use vertical to control the Z voltage. Record the Z voltage or height sensor. That's enough. Quite easy. And so in old days, we think the contact mode is the fastest one in electronic loops because loop is so easy. But in nowadays, our electronic loops, they're so fast, so we don't consider this as an advantage anymore. And then it has some big disadvantage is that the sun tip is always touch on the sample. It will give us a big friction, and the friction will give us some the things we don't want. If some of you have imaged particles, you can see some phenomena that you don't see this particle during imaging. That's why, because your tip movement, you just drag your samples moving back and forth. So because the sample is moves due to the friction, and so how to do that? How to achieve a good resolution? You have to make your force to be as small as it can, so it tracks the surface rather than push the surface. So the big disadvantage of the contact mode is the friction. We need to remove the friction. So to remove the friction, we have two modes. The famous tapping mode. So this kind of tapping mode is its principle is slightly difficult than the contact mode. It's the major goal of the tapping mode is we want to reduce the friction. To reduce the friction, let's look at the friction comes from. So the friction, it comes from a friction coefficient and the normal pressure. You have so in our high school, our teacher told us you want to get rid of the friction. You need a absolute smooth surface, but of course we all know absolute smooth surface does not exist. So to get rid of friction, you can only get rid of that. To get rid of the normal pressure. That means we want our tip to move our surface without touch it. But no, that's not exactly can be achieved because we want our tip to trace the surface. We cannot really get rid of the pressure. We cannot really get rid of the contact. So we use this tapping way. We let our tip to tap on the surface, and its contact on the surface is not constant. It's just inconstant. The contact. So by using this tapping, we can say when it's moving the surface, its friction is almost reduced. So in such way, we can get rid of the friction. That's the major advantage of the tapping mode. And then we need to do some change. For the tapping mode. For the tapping mode, we make the tip to vibrate on the surface. And we all know, have some idea that if our probe is vibrate, if our AFM cantilever is vibrate, and its vibration will give us an amplitude. If we put a sample get closer to the tip, this sample will damp or it will affect this tip vibration. As such, it can change the amplitude. So that means if the distance between tip and the sample increased, its amplitude will decrease. So we set up a relationship, we set up another function for the distance between tip and the sample by this kind of amplitude. So for the tapping mode, we can do this way. We control the amplitude to be constant. If the sample is getting too close to the surface or the distance is too small, it will reduce the amplitude. It's almost opposite as this one. So we will have another loop. So let's look at the same bump again. It's a bump. We define it moves from A to B. We'll say D, E, F. Okay? Our goal here is we want to make the amplitude as a constant. So this value is the amplitude. We want our amplitude to be a constant. So we call this constant set point again. From A to Z movement, our amplitude should be a constant. So this one will be a line, and as such, the Z voltage will be a flat line. And again, when the tip reaches the C position, the distance between C to D is large. It's too large, it increases. It will reduce the amplitude. So at this point, the amplitude will decrease. And then our Z voltage understand, okay, the tip is too close to the surface. We need to apply larger Z voltage. So the Z voltage will increase. And at this point, the amplitude will come back to its set point. And then the tip is here. It should go to the E point. And to reach that, our Z voltage should be a constant. And then when the tip reaches the E point, there is no sample beneath E, so its amplitude, so its distance will decrease. So the amplitude at this point will be large. And then we know we need to reduce the Z voltage slightly and get the image. From the Z voltage, you can get the topography, either from height or height sensor. And then this thing is the so-called amplitude error. Right? That's the contact mode and the tapping mode. And the contact mode and the final topography we get is the same. We all need the two C's. The Z movement is fast and the XY movement is slow. We all require that. That's our the images stuff. And then for contact mode, we are looking at deflection error. And for the tapping mode, we are looking at the amplitude error. And it's changing, it's just opposite. Right? That's our tapping mode. Okay? So for the tapping mode, it has a big advantage that it reduces the friction. So it will not change the shape, or it will not damage our samples. It's good. But it has one disadvantage. To contact mode, we are looking at the vertical. And this vertical, we know is just proportional to the force. But for the tapping mode, we are looking at some amplitude. And we know this amplitude should be related to the force, but we don't know exactly what the force is. So the biggest disadvantage in tapping mode is the force in the tapping mode is unambiguous. So it's kind of hard to define what's the real force in the tapping mode. But that's why when you're looking at the textbooks, it gives you a long mathematical equations to get the relationship between the force and the amplitude. That's the reason. So in the tapping mode, it's hard to get the real mechanical properties in quantitatively. That's our tapping mode. Okay, so do we have something to kind of achieve the thing we want? We get rid of the friction, or we can still keep a good measurement for the force. That's the so-called the peak force tapping mode we are looking for. So the peak force tapping mode is the same. It's similar as our tapping mode that we make our tip to jump on the surface, and when it jumps on the surface, we have the so when the tip is moving up and down, down and up on the surface, so we let the tip close to the surface and then away, and then during this movement, we look at the vertical. When tip is get close to the surface, before it touches the surface, of course, it will has no force, so the vertical will be 0. Once the tip touches the surface, there will be a force between tip and the sample, and it will give us a vertical. And then we increase, we drag up the tip, and then force will reduce. So we will get this kind of force distance curve. And this force distance curve, we can say, okay, its vertical is changing. And then at this point, we call this peak force. At the peak force, we know, okay, the tip touched the surface at its maximum force. Okay, if we do not read the amplitude, but we read the peak force, it gives back some similar things as our contact mode. So let's say the tip is moving up and down on the surface, but at its lowest position, it touched the surface. If we control the force at its lowest position as a constant, it's almost the same as our contact mode. But the tip is jumping on the surface, not keep moving on the surface, not scratching on the surface. So this movement get reduce the friction. But it's the same as the contact mode. We can again calculate the vertical to get the force. That's the peak force, that's the so-called peak force tapping. And with the peak force tapping, we can combine the advantage between the contact mode and the tapping mode. Of course, it has its own background, and we will go through that on Thursday. It's when we're talking about the peak force treatment, we will give details about the peak force tapping mode. Okay, so the peak force tapping, the peak force tapping mode and the tapping mode are the two most common modes you will use in your imaging, and both of them get rid of the friction. Both of them can give you a topography without damaging the surface. So mainly you will use these two, tapping mode and the peak force tapping, and the contact mode, no, is not our routine imaging mode for the topography, but it has some difference. First, the most important difference is the peak force tapping mode can give you the force. So that's why from the peak force tapping mode you can get the quantitative mechanical stuff. That is the peak force QNM. For tapping mode, it's hard to get the quantitative mechanical thing. You need to do a long calculation from the phase. That's another difference. Okay, so for the tapping mode and the peak force tapping mode, the major principle is not the same. One is on amplitude, another one is on vertical. Okay, so these details we will go through that tomorrow when we're talking about the image scales. And for the peak force tapping mode, we develop a scan assist mode. This scan assist mode is just it's just an algorithms, and this algorithms is just let the software to calculate to define the force applied and the Z movement speed. The stuff is for you. So most of you using the AFM, you will just use the scan assist mode. Behind that is just the peak force tapping mode. Okay, so now let's just say how good the scan assist mode is. Okay, so we will just in the afternoon you can practice on the scan assist mode again to say how it works. Okay, so for the AFM image modes, we have the three basic image mode: contact mode, tapping mode, and the scan assist mode. And for different modes, you will have a same topographic image, height for height sensor, and then you will have some arrow channels. And we were talking about what this arrow channel means when we're talking about feedback tomorrow. Okay, and the spectral mode is about the force curve, and we will go through that on the 4 days on Thursday. Okay, so that's about the major stuff we will discuss today, and basically we just try to give you a big picture of our AFM principle. We separate X, Y, and Z, and we use we use the tip movement at the Z direction to control the distance is a constant. This distance can be represented by the tunnel current or the vertical. Okay, and how to read this kind of thing? We have the contact mode, tapping mode, and the peak force tapping mode. And in our hands-on session, we will just discuss the 2 major groups. One is the XY, and another one is the so-called the Z direction movement. Okay. Okay, I think that's all for today's discussion. And if you have any questions, we can discuss later or during the hands-on sessions. And if some of you have prepared your own samples, we can say maybe today or on later hands-on sessions, we can just use your own to do the practice. Okay? Okay. Thank you. I think that's all for tomorrow's theoretical session. Thank you.